So welcome to MathStat341 Lecture 7. I'm using again slides from the previous talk. I really felt no need to go through and change these. What I want to do is I want to continue giving you a sense of what we can do with probability. Why are you spending an entire semester learning these techniques? What kind of problems can you solve? We're going to start by looking at some deterministic problems, which is just a matter of computation. And then the reason they are interesting for us is because there will be random analogs of those. And that's the one that's going to be very interesting. All right. So we'll look today a lot about continuous systems, continuous models. We'll talk about how to solve them. You may have seen the word stochastic in either some of your other classes or at least in the course catalog. For future classes you can take. We'll mention a little bit about that. We've seen it already. We'll discuss some general solutions, and then I'll talk a little bit about some research I've done with several undergraduates over the years at Williams. So if any of you are interested in summer research, we have a wonderful program, this small summer program here, where freshmen, sophomores, juniors are able to come and look at math research problems, stats research problems, and try to get a sense of, is research right for me? And it's okay to find the answer is no. You will still get valuable skills in terms of how do you read technical articles, how do you write a paper, how do you give a talk, how do you try to prove something new. All right, so continuous systems. How many of you have taken differential equations? Okay, this is greater than 0. This is more than often happens when I teach this class. This is wonderful. So you might have seen a little bit of differential equations in calculus. They keep changing the curriculum a little bit as to what is done. Thankfully, plotting functions by hand seems to have been removed from the curriculum, which has opened up the ability to actually talk about things that matter. So let's look at the differential equation f prime of x equals a times f of x with the initial condition f of 0 equals c. And we want to solve it. And this is a first order differential equation. It has just one derivative. We only need one initial condition to solve it completely. Any value of a that might make this problem a little bit easier? Yes, 1. And if you want to make the problem really easy, 0. Okay. I'm not going to really look at f prime of x equals 0. That means there is no motion. You are always where you are. But f prime of x equals x, you might have seen that before. That's just the exponential function. So the solution is just c times e to the x. And that will work so that when x equals 0, you do get back f of 0 equals c. More generally, if we have a times f of x, we'll get c times e to the ax. So this is a nice function. It turns out it's very useful. It turns out trig functions are also related to the exponential function, which we might talk about later in the semester if there's time and interest. And what's nice is there is no excuse in a class with me to get a differential equation wrong, to get an integral wrong. I will be very upset if you get any of these wrong. If you can't do them, that's fine. If you think you have an integral and you think you did it correctly, what can you do? Differentiate. Differentiate. And oh, I didn't get what I started with. Something must be wrong. So if you can check your work, do so. It's nice. If I believe that this is my solution, well, I can check and see, does f prime of x equal af of x? It does. That doesn't prove that I haven't made a mistake, but it's a strong indication. I also have to check the initial conditions. So what if we had two derivatives? What if we had f double prime of x is af of x, is af prime of x plus bf of x? This should kind of look similar to the Fibonaccis and the difference equations we looked at. With the Fibonaccis, fn was equal to fn minus 1 plus fn minus 2, 2 time steps beyond. And so we saw that for the Fibonaccis and recurrence relations, they had this geometric growth rate. It turns out your geometric exponential, similar, it's just slightly different ways of phrasing it. We have the same thing going on here. We could try an exponential function. It worked so well before, let's try it now. So if we try f of x is e to the rho x, where my rho is now a free parameter. If I plug that in, I get rho squared e to the rho x equals a rho e to the rho x plus b e to the rho x. I can remove e to the rho x everywhere. Why? Why can I remove the e to the rho x?
Because it's shared between all the terms.
Almost. You're very close. What you have to make sure, it's not enough that it's shared.
Multiplied.
No, almost.
It's not 0.
It's not 0. So in this department, now if you were in physics or economics, that would be fine. In fact, they wouldn't even have to even be the same things in some of the departments here. But in math, we always have to make sure that it's not 0, because if it's 0, then I can multiply by anything and it's still going to be true. So because the exponential function is never 0, we can remove it. If you look at it, the e to the row x, I can write that as e to the row raised to the x. So e to the row is functioning like the r that we had in the Fibonacci's before. And so we get a Captcha's equation very similar to the Fibonacci's. We get rho squared minus a rho minus b equals 0. It's got roots rho 1 and rho 2. So we get a general solution is going to be some number alpha e to the row 1x plus beta e to the row 2x. And then you can check and see that it works. We have two free parameters, alpha and beta. The row 1 and row 2 are forced upon us. And you would get those by the initial conditions. Maybe I tell you your value at 2 moments in time. Or maybe I tell you your value and your derivative at 0. That's frequently how it's given. So in general, we can do more variables. We could also use m is af plus bg of x, and g prime is related to cf of x plus dg of x. You might have seen something similar to this with the predator-prey equations. Has anybody seen predator-prey? I imagine you only have a world of rats. And the rabbits are going to grow without. Now you well, if the wolves eat too many rabbits, then what happens to the wolves? Right, so what will happen now if you don't have enough rabbits to the wolf population? It goes down, which then allows the rabbit population hopefully to go back up, as long as you haven't taken away so many rabbits that you're in danger. And I still remember I took a differential equations class where they had a model for humanity, and unfortunately, where we were in phase space, we were going to go extinct. And then they said, I still remember this, a fleet of benevolent alien warships lands and starts harvesting humans. How many humans must be harvested a year to prevent the population from going extinct? And just pushing in the right things. If you are doing a predator-prey, and if maybe F is the number of rabbits and G is the number of wolves, you're going to want to think, what should the signs of A, B, C, and D be? There should be some interpretation, some meaning. Well, if F is the number of rabbits, maybe A should be positive. The more rabbits I have, the more rabbits I get. And if G is the number of wolves, maybe B should be negative. The more wolves I have, the fewer rabbits I have in the next period of time, because they eat each other. Always tell stories. When you see a model, get some sense of what the parameters should be. So how do we solve something like this? Well, we can try to go back to things we've seen before. This is the general theme in mathematics. How can I make this look like something I know how to do? Well, I've got my system of equations. I've got my f prime and g prime. And in linear algebra, we learned how to solve for one variable in terms of another. So if you're comfortable with matrices, you can use matrices. If not, if I have things in terms of x and y, I solve for y in terms of x. I then feed that into the other equation, and now I have an equation for x. I solve for that, and then I feed that into the equation for y in terms of x, and then I get that. So what I can do here is I can write g of x is equal to 1 over b f prime of x minus a over b f of x. I'm getting that by looking at the first equation and just solving for g. What am I assuming right now? B does not equal 0. So I'm assuming B does not equal 0, and it generally does depend on both of them. And now that I have an equation for G, I can take the derivative of that, and I'll get my derivative of that is equal to something times F plus all that other stuff. And now everything only involves F. So when the dust settles, I get a second order differential equation. F double prime equals crap times F prime of x plus other crap times F of x. This is the same form as what we just solved a moment ago. We then just guess F is equal to e to the rho x. We'll get two different values of rho. And we can now solve for F, we can solve for G. We can write this into matrix form. We'll let B be our vector F of x, G of x. A will be our matrix A, B, C, D. Formally, we have F prime of x equals A F of x. Now we have V of x. V prime of x equals A V of x, where A is now a matrix. And this is the idea of mathematics. Reduce to something you know. The solution before was e to the ax, where a was a constant. Now the solution is e to the ax, where a is a matrix. And it turns out you've got to figure out now, how do you deal with the exponential of a matrix? Well, if you go back to how do we define e to the x, there's two definitions. There's the one that people love who do compound interest, the limit of 1 plus x over n to the n, and then there's the infinite sum. And if you take the infinite sum, this actually makes sense as long as A is any square matrix. And because k factorial is growing so rapidly, it will converge for any value of x. And so you can justify the 2-by-2 differentiation, and you can actually solve systems of equations like this in matrix form. So if you've taken linear algebra, here's a way to soup up the linear algebra and do some useful stuff with it. Now, unfortunately, it's actually hard to work with matrix exponentiations and multiplying them together. I'm not going to go into details, but just a little warning. Can anybody tell me about the Battle of Trafalgar? This is Williams College, right? We're supposed to be learned in a variety of subjects. When I was interviewing, I was actually given a Shakespeare quiz in the math department. Well, it's the math department, but it was a mathematician who was questioning me on Shakespeare, so I'm not going to blame the statisticians. Fortunately, I knew enough Shakespeare to pass the questions.
Was it based on math within Shakespeare?
No, it was quotes from Julius Caesar. I think it was Jan Cassius has a lean, hungry look. I trust him not, such men are dangerous. I was also quizzed on the shirt I was wearing. And I said, the reason I'm wearing this shirt is it was a dark green shirt, is I have a young baby who's about a year old, who often drools on me, and I have to shovel up my car to drive 3 hours here. I wanted something dark, so hopefully you can't tell the... Turns out it wasn't too bad, to be honest. Everybody know about the Battle of Trafalgar, one of the most important battles in the history of the world. Anybody at least know who the combatants are?
Give us a time frame.
Early 1800s.
Napoleonic.
Napoleonic Wars. So it's the British against the French and the Spanish. Okay, who do you think won? British. It's a naval battle. Okay, for years Britain was the master of the sea, and for a while they had a policy that they had to be strong enough to fight any 2 navies simultaneously. And then by the time World War I came around, they could no longer do, we'll take the next 2 on ourselves. And there was a huge naval armaments race before World War I. And I think at one point, the Admiralty wanted 4 battleships or dreadnoughts built. The Admiral of the Navy wanted 6, and they compromised on 8. But just as they were having the discussions, they realized, oh my God, the situation is far more perilous than we feared. Germany is arming very fast. We need to divert resources to these very quickly. So Wikipedia has, not surprisingly, a really nice description of what's going on. This basically ended Napoleon's chance of successfully invading England. So there are a whole slew of people who have tried to take down England and Britain, who have uttered words of, if we could just control the channel for a day and land our troops. And the goal of the Navy and then later the Royal Air Force is to make sure that nobody gets that day. And so this was a monumental battle. And so let's let RT and BFT be the effective fighting values of the Red Fleet and the Blue Fleet. So I will be very careful what I say, but this is the 21st century. We live in politically correct times. Some people might feel bad if they are affiliated with the losing side. So when they celebrated the, I think, 200th anniversary of the Battle of Trafalgar, rather than having the British against the French and the Spanish, they had red versus blue. Okay, so we will just leave it as red versus blue. If you want to think in your mind of one of them being one side or the other, that's fine. All right? But we want to know who's going to win a battle. Well, it may not be the case that each ship or each crew is as good on each side. The British were actually better sailors and they had slightly better ships. So when you want to look and see how is the rate of the Blue Fleet changing? Could the Blue Fleet be getting larger because of blue boats? Are they going to be shipbuilding in the middle? No. So the Blue Fleet is going to be decreasing, and it makes sense to say that its decrease is going to be a function of the number of red boats that are out there. And similarly, the red boats are going to be decreasing based on the number of blue boats. And the N and the M will be related to the effective fighting effectiveness of the 2 sides. This is a very deterministic model right now. Real warfare is not like that, where you say, we've done the calculations, according to these calculations, we win. So you should Now, the other thing is, it is possible back in the old days to actually have people take over votes from the other side. So we'll leave complications like that for now. We know how to solve this, right? What do you expect the solution to look like? You know, we should have exponentials. What should be happening to the number of ships as a function of time? Decreasing, right? If you're having a battle, probably either decreasing or maybe staying the same if you're really good. But probably both sides are decreasing, and we'll go until one side goes all the way down to 0. So if we take derivatives again, we get the second derivative of b is minus n r of t. Well, we know what r of t is. We can solve for that. So r prime of t, we know what r prime of t is. So we get a differential equation, and we get b of t and r of t. And we have two factors, a beta 1 and beta 2, and an alpha 1 and an alpha 2. But if you look at this, you can tell me the value of one of the betas and one of the alphas. Which beta do you know its value? So you want to get to the point where you can look at formulas. Yeah, what is beta 1?
0.
0. Because you have beta 1 e to the square root of nmt. This is an exponentially growing term. If beta 1 is not 0, then the longer the battle goes on, the more ships Britain gets. I'm sorry, the more ships Blue gets. Okay? So clearly, beta 1 and alpha 1 have to be 0. That's the only physically reasonable thing. And this is great when you can make arguments like this in your model. You can look at the ratio of b prime over b. It turns out that's the same as r prime over r. And b prime is how many ships Blue is losing. And then a good unit to look at that is also relative to how many ships they have total. And when you solve this, you get nr squared is nb squared. And this is called the square law of the effective value of the forces. And so Nelson was outnumbered. So, you know, this is essentially what Nelson's battle plan was. Is the French-Spanish Armada had more ships than he did. And his idea was to attack in the middle and try to split the force against him into two components. And he would have his main fleet engage a large subset of the French-Spanish Armada, and in a smaller part of his fleet, do a delaying action and just keep the other ships distracted and occupied away from him. And once his main force defeated the main force, then they would swing back and get the rest. And so the original battle plan, I mean, he was splitting it actually into threes. What he finally did is actually pretty close to what the math says. So if you use the square law, he had 40 ships, the French and Spanish had 46. And so if you look at like, if you assume equal fighting power, he's a little bit outclassed. But he split it so that he had 8 of his ships dealing with 23 of the British, I'm sorry, 23 of the French and Spanish, and another 23 of his ships dealing with 32. And no, I'm sorry, he had 32 of his ships dealing with 23, and he had 8 of his ships dealing with 23. And when you break it up like that into the two small engagements, he actually now has a small advantage. Now, how does things actually go? This is one of the most decisive naval battles in the history of the world. So they defeated 33. The actual battle was a little bit different than the preliminary. You know, not all the ships were able to make it. He had 27 ships versus 33. The French and Spanish fleet lost 22 ships without a single British ship being lost. This is wonderful examples of how a lot of people just instinctively know a lot of good mathematics. If you've ever seen a baseball game or a football game or any game where you throw the ball and catch, this is a calculus problem. It's the orbit of a ballistic. If you ever see a major league fielder or football receiver taking out a piece of paper and start doing some calculus equations to predict where they should run, I will give you extra credit if you can give me that video. Or if you can see them at home doing these calculations. After a while, you just instinctively know where things are. Now, that doesn't mean you can't do better if you know more math. But people can often get close to the optimal solution just from experience, and you just learn things. All right, so monuments to Nelson. As I said, 0 of 27 ships lost to 22 of 33 for the French and Spanish. All right, now, the problem with this is not a really good topic for probability. This is completely deterministic. Where probability comes into play is the fact that we were assuming a constant model for how things evolve. And we talked about this with the Leslie matrices last time and the population of whales. And we said it's absurd that no whale dies until they turn 4. It's absurd that the whales always reproduce at the same time in the same numbers. And we then said, rather than having a fixed matrix, now we're going to have a matrix of random variables. And you can do the same thing here. Rather than having a system of equations with a deterministic matrix, we can now have something that's stochastic and that evolves. And so what I want you to get out of this lecture today is, where do you go after this class? What can you do with the materials you're learning? We can go from these simple models to give us some intuition to the more complicated deterministic one, more complicated stochastic ones. All right. So for the remainder of the time, I want to talk about some research I've done with students here. It's a great way to motivate some of the combinatorics we're doing, to motivate the central limit theorem and some of the results we're going to see. And these are results that are done by students. Right, so the first is the Fibonaccis. I'm defining them slightly differently than before. I'm defining them as 1, 2, 3, 5, 8, 13. I don't have the double 1. And it turns out it's very important that I don't have the double 1 because I now have a beautiful theorem due to second order. Every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. If I had the double 1, I would lose uniqueness. Which one do I use? I could use either one. So let's take 51. How many of you have heard of the greedy algorithm? Right. Greedy algorithm is one of the greatest ideas in the history of humanity. What it basically says is that every moment in time, do what's best. That does not guarantee that you will always get to the best place, but it's not a bad strategy. And frequently, if you do what's best at every moment in time, you will end up at a good place. How many of you like to have fun? I'm a little scared that not every hand is going up right now, but that's okay. You don't have to like to have fun in this class, although I hope you do occasionally enjoy the lectures. But I'm guessing that you might have things you like to do in your life other than classes. So you probably decide, I'm going to spend some time doing fun things. If you are trying to maximize your happiness over life, what you could say is that every moment in time, I'm going to do what makes me the happiest at that moment. Okay? I leave it as a theoretical exercise to figure out why this is a bad thing to do. Do not try to do this. Just say, hey, Professor Miller, you were right. This was a bad idea. And I don't want to have this conversation after the first exam. Okay? So if you do locally what's going to give you the greatest happiness for every moment in your life, you're not going to have a great life. Unless you start off at a really high place. You're like, you have multiple billionaires in your family tree, then you're going to be okay. Most of us, we're not going to be there. So you have to say, well, I'd like to do this, but I need to do this now. And you have to figure out, how do you want to allocate your things? The greedy algorithm, however, frequently does give you the best. So what I'm going to do is I'm going to take 51, and I'm going to say, well, what's the largest Fibonacci number less than equal to 51? 34. So I'll write 51 is 34 plus 17. And you can see that 34 has now lit up in red. Okay? 17. What's the largest Fibonacci number less than equal to 17? 13. I'm doing the greedy algorithm. At every moment in time, I'm pulling out the largest Fibonacci number I can. Now 4, well, the largest Fibonacci less than equal to 4 is 3, and then 1 is already a Fibonacci number. And so there's my decomposition. And if I'm decomposing, if I ever had two numbers that were adjacent Fibonacci numbers, then I'm a moron. If I had 51 is 34 plus 21, well, I had 34 and 21 next to each other, I could have thrown away their sum. So because I'm always throwing away the largest number I can at the time, I can never throw away two consecutive Fibonacci's. So with a little bit of work, you can show that this always terminates. And with a little bit of work, you can show that this decomposition is unique. That I can't write my number as another sum of non-consecutive Fibonacci. Maybe I don't start off with 34, maybe I start off with 21. So you can show that there is one and only one decomposition. This is the standard way the theorem was proved. A couple of years ago, a colleague here was giving a talk on this, and he was mentioning related problems. It was using number theory and continued fraction. I'm supposed to be excited. I wasn't, because I also teach probability and do probability. And I realized this is not a number theory problem in combinatorics. I'm sorry, this is not a number theory problem in continued fraction. This is a probability problem in combinatorics. And the only paper I had on me was from the Children's Center where my son had just been bitten by his best friend. And so I quickly jot down some notes that, actually, you can recast all of this in terms of combinatorics works and bypass all the number theory. Now, we do like to do applications. So I will give you the most absurd possible application of the Fibonacci numbers in the world. I learned this from Carl Pomerantz, I believe learned it from Andrew Granville. If you can find a worse, more absurd application, I'll give you extra credit. Right? 83 is 55 plus 21 plus 5 plus 2. 51 miles is almost 83 kilometers. Why?
Because there's 1.6 ground kilometers.
Yes. Each Fibonacci number is approximately the golden mean more than the previous, and the conversion factor between miles and kilometers is almost the golden mean. So if you shift every Fibonacci number, its index up by 1, that's almost the same as multiplying your number by the golden mean, which is almost the same as converting. Now, the larger your number is, the better this is going to be. If you want to try to convert 4 from miles to kilometers, this would be very bad. Do 400 miles to then kilometers, and then divide by 100, and it'll be pretty good. So if you need to convert from miles to kilometers, what you can do is write down the Zeckendorf decomposition, shift all the indices, and that will be a pretty good approximation. Okay? If you can find a more absurd application, please let me know. All right. So the golden mean is 1.618 approximately, and 1 mile per kilometer is 1.609. It's not that bad. All right. So the first is the central limit then. So I'm going to show you a new way to prove Zeckendorf's theorem, which is a lot more work. And the question is, well, why would I want a proof that is more work than the simple proof? It's because it gives you more information at your disposal. And what you can do is you can look at what is the distribution of the number of summons in my decompositions. Now, it's extremely important to compare apples to apples. So what I want to do is I want to look at all numbers between the nth and the n plus first Fibonacci number. And the reason is these numbers will all be about the same size, and they will all have Fn as their first summon. If I look at numbers that are, let's go back to, okay, so here we have the Fibonacci numbers up to 89. The next number is going to be more than 100, it's going to be more than 89, it's going to be 144. If I give you a number up to 100, I'm never going to have a number larger than 89 in its decomposition. And since I can't have two adjacent numbers, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 10 numbers. What's the maximum number of summons I could have if my number is at most 100? 10, yes, but you can actually do better than 10. Because you can't be adjacent. So you have at most 10 summons, but you can also improve it to at most 5. So if I want to compare the distribution of the number of summons, well, if my number is small, I don't have that many summons available. And so by looking at numbers between Fn and Fn plus 1, these numbers are now roughly the same size. The other thing is the Fibonacci's are growing exponentially. If I started all the way at 1 and went from 1 to Fn, almost all of the numbers are in the last few bands, and so the small numbers don't really dilute things that much. But you want to think about how do you compare things. And this is a key idea in probability and statistics. We want to compare similar objects, apples to apples. And that's why we'll localize. And here's a plot of a distribution of the number of summons. So when do you think I first gave this talk?
2010?
Yeah, it's either 2010 or 2011. It's one or the other. I think I first gave the talk in 2010. And so F of 2010 is about 10 to the 420. So I'm looking at 420-digit numbers. Okay? I am not doing a brute force exhaustive analysis of all numbers between F2010 and F2011. I'm just doing a random sample. I'm doing maybe a million such numbers. And you see a Gaussian, and it turns out it does converge to a Gaussian. This had been proven before us. My students came up with a new proof, and then we actually extended it to other settings. Now, the following is just a fun fact. There's another way to interpret the Fibonacci numbers. And this is similar to when we did proofs by story. There's a tremendous value if you could look at things different ways. So it turns out the Fibonacci numbers can be defined as the unique sequence such that every integer can be written uniquely as the sum of non-adjacent terms. So you start off with the number 1. I then have to add the number 2. Can I write 3 as the sum of non-adjacent terms in my sequence? No. So I have to add 3. Can I write 4 as the sum of non-adjacent terms in my sequence? Yes, 3 plus 1. Can I write 5 as the sum of non-adjacent terms in the sequence? I have to add 5. Can I write 6? Yes, 5 and 1. Can I write 7? 5 and 2. Can I write 8? No, I have to add 8. This is an alternative definition of the Fibonacci numbers. And then you need to show that this is the same as the Fibonacci definition that you're used to. And what this means is that you can now pass from knowledge in one perspective to results in another. All right. So you can do 13 and you can continue. All right. So there's a lot of different ways to generalize. I don't really want to go into those now. I want to talk a little bit about how, and we were guilty of this as well, you often look at the wrong thing. So we can look at a more general recurrence relation. So instead of just fn plus 1 equals fn plus fn minus 1, we could have a whole slew of things of fixed length with coefficients. It turns out we need the coefficients to be integers, non-negative. We actually need the leading term to be positive, or there's some technical troubles. It turns out that there's a generalization of a legal decomposition, and it turns out that there's a generalization of the central limit theorem. Let's look at a special case. We should have done this before we did the Fibonacci. We did this in the moment. Yes.
Is it legal decomposition?
So I don't want to say in detail, but it's a generalization of for the Fibonacci's, you couldn't have two things that are adjacent. The short answer is I can't use my recurrence relation to remove it. And that's what was going on with the Fibonacci. We could use the recurrence relation to remove two adjacent things. Okay, so let's look at the similar recurrence relation. Hn plus 1 is 10 times Hn. This is just each number is 10 times the previous. So the numbers are powers of 10. A legal decomposition basically just means I'm writing a number in decimal. Why do we like decimal so much? Why do we like base 10 so much? No good reasons we should throw up our hands in frustration? Why do we like? We have 10 fingers, right? We do have 10 toes. We couldn't go base 20. No, it's very awkward to use your toes. That's why we stop at 10. The Babylonians had reasons for liking 60, but we like 10. Do you have to do things base 10? No. But for us, it's convenient to do things base 10. We have a lot of familiarity with decimals. So a legal decomposition just means I write my number in decimal notation. So I'm never going to have 3, 0, 11, 5. How many of you have seen hexadecimal? So then you'll use some letters. You go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10. Okay? How many of you have seen binary? So you know that there are 10 types of people in the world? Those who understand binary and those who don't. So if I look at my legal decomposition, what is the analog of what I was doing before? It's counting how many summons I have. Well, it's just going to be counting the digits. Each AI can be from 0 to 9, except for the leading term, which has to be from 1 to 9. So if I want to try to see what's the distribution for the number of summons, well, let's look at the distribution for the number of summons in this special case. And so the first term is always going to be some number between 1 and 9. And everything else is going to be between 0 and 9. It's as likely to be a 1 as a 2 as a 0 as a 9. Think of it as rolling a 10-sided die. So I am summing the rows of like n 10-sided dies and 1 9-sided die. Screw the 9-sided die. If n is large, it's not going to really change things. So we showed in the last lecture what happens when you keep summing uniform random variables. It converges to a Gaussian. Foreshadowing, right? Now we can use that here. We haven't proven it yet, but when the central limit theorem is proven, we will see that that should converge to being normally distributed. And we can actually calculate what is the mean, what is the variance, and there's the central limit theorem. And so this tells you that the recurrence relation, Hn plus 1 is 10Hn, leads to Gaussian behavior for the number of summons. We expect maybe the same thing will be true for the Fibonacci's. That maybe this is a general phenomenon for recurrence relations. So again, I was talking with a student about how students take notes and how students pay attention in class. Almost surely we haven't talked to you at all about how to take notes and pay attention in class. So this is probably not a bad idea. You have to take notes and pay attention in a way that works for you. When there's books and there's slides, it's how much do you want to write down? When I was a student, I wrote down everything. If the professor wanted to know what did they say 13 minutes in 4 classes ago. Oh, I can tell you it's right here. This is what you said. And actually, no one laughed at that joke. I had detailed notes. If you know how to LaTeX, I can actually LaTeX in real time. And I was once at a conference, it was like dueling banjos. Next to me was somebody else who could LaTeX in real time. And we had a little contest to see who could do better. I'm not going to say anything with the recording, but I'll make some gestures. So, how should you take notes for something like this? You want to think about what is the big picture. The details you can read later. Your big picture is look at simple cases, build intuition from simple cases, look at the right object, get the right sense to study things. All right. So for the Fibonaccis, we could also talk about the gaps between summaries. So let's say I have F1 plus F8 plus F18. Then the gaps are 7 from F1 to F8 and 10 from F8 to F18. You could also talk about maybe the gap to the first one, to the F1, but that's only one more gap, as n is very large, the number of gaps is so large it's not going to really matter. And you could ask, let's let Pn of G be the probability, that's a good word for a class like this, the probability that we have a gap of length G. What's the probability we have a gap of length 0 in a Zeckendorf decomposition, that we have a repeated summand? 0. What's the probability we have a gap of length 1, that we have 2 adjacent summands? 0. So we know, Pn of G is 0 if G is 0 or 1. And then the question is, what is it for other values? Does the limit exist? Turns out that the answer is yes. And you can analyze it. There's lots of different ways. I plotted on the left a histogram of how many times we have gaps of different sizes. If you look at that, can you see its geometric decay with a ratio of 1 over the golden mean from one to the next? Can you look at the one on the left and see that? I can't. A huge part of this class is how do you present data in a way that is convincing and illuminating. So the theorem says that the gap converges, if you look at the average sense, and I don't want to go into all the details, to 1 over the golden mean to the k, where k is greater than or equal to 2. So as a nice exercise, it's a probability distribution. It should sum to 1. So you should show that the sum of 1 over p to the k goes from 2 to infinity, sums to 1. What I did on the right, we have this nice solid line and a bunch of blue dots, is I plotted the ratio of the probability of a gap of size G divided by the probability of a gap of size G plus 1 from looking at my histogram. And you can see that it looks pretty level, that each time I seem to be going down by about the golden mean. And then as you start getting further and further out, you start having fewer elements in each bucket, and then just one point being added or not will make a huge difference. Given that we are moments away from the Sox being eliminated from postseason play, I will talk about the greatest baseball season of all time, which is any Red Sox fans here? 2004. In 2004, the Red Sox were trailing the Yankees in the best of 7. They were down 3 games to 0. First team to win 4 games advances. No team in baseball history had ever come back down 3 games to 0. It had happened a small number of times in basketball and hockey, never in baseball. Why? Any reason?
So you have to win 4 games in a row.
Well, but that should happen if the 2 teams equal, 1 out of 16 times.
But it's less than 1 out of 16 because the team that lost 3 times probably is.
Is what?
Probably worse.
Yeah, so there might be a reason you're down 3 games to 0. The assumption that the 2 teams are equal. Well, let's see. Loss, humiliating loss. Maybe you're the worst team, and it's not a 50-50 proposition. There's also psychological things, but there's also just the number. So we got a little argument, you need 20 or 30 points to be confident that the central limit thing was kicking in. It had only been about 25 times the team had gone down 3 games to 0 in a best of 7 series in baseball. Well, if you expect to come back if the 2 teams are equal 1 out of 16 times, you would expect to see somewhere between once and twice a team coming back. Seeing 0 is low, but it's not so abnormally low that you would be shocked. And then once the Red Sox actually came back, there you have 1 out of 26. It's a little bit low, but it's not terribly low. And you want to get a sense of how surprising is data. And so over here, when you look at the chart on the right and you see that it's no longer so great as you get further and further out, well, missing 1 or 2 values now is going to have a huge impact on these probabilities. and I don't trust the results that far out. So again, big theme for the class, when you look at a plot, where can you be confident? Where are you less sure? The other thing is, I will not ask if you've ever had a sadistic calculus professor. I will just assume that at some point in your life, you have had somebody who's giving you painful derivatives to do just because they like to see you scream, okay? And you might have to take the derivative of the exponential of an exponential. Here is a situation where the exponential of an exponential actually arises. You can look at what is the distribution of the longest gap between sums. This is a probability problem. It actually turns out to be related to, if I flip a fair coin, what is the distribution of the longest gap between tails or between heads? What if the coin is not fair? What's the distribution? And it turns out you have something that is incredibly strongly concentrated. You know, the probability that the longest gap is at most some function f of n, you've got an exponential of an exponential. And so this is just show you that some of these functions that you've seen in calculus, they actually do arise. And we will see exponentials of exponentials and other problems later in the semester. This is why it's nice to have techniques that allow us to handle stuff like this. All right. So I want to talk a little bit about combinatorics. How many of you have seen Sesame Street? All right. So we'll be using the original class Cookie Monster who likes cookies and is always deemed to eat cookies, not the politically correct Cookie Monster that sings about vegetables and cookies being sometimes food. All right. We will do the original class. Extra credit right now to anybody who can tell me the original color of Oscar the Grouch. It's not green. Yes. So I'll let you look that up. He was not originally green. The number of ways of dividing C identical cookies among P distinct people is C plus P minus 1 choose P minus 1. So I often say, you imagine you're a graduate student and all the graduate students are distinguishable, but the cookies are not. I'm sorry, all the graduate students are distinguishable, but the cookies are identical. How many ways can you divide cookies among grad students? If you're an engineering grad student, this may not be a reasonable assumption. There are some professors who just treat their graduates as almost interchangeable parts in their labs. We will assume you're at least in a discipline where the professor knows who you are. And we want to know, how many ways can we divide the cookies? So here's the proof. Imagine you have C plus P minus 1 cookies on the line, and Cookie Monster shows up and eats P minus 1 cookies. How many ways can Cookie Monster choose P minus 1 from C plus P minus 1? Well, that's the definition of the binomial coefficient. And it turns out that there is a one-to-one correspondence between this and the number of ways to partition C cookies among the P people. And this is the key idea in a lot of these results in combinatorics, which is a lot of discrete probability. Tell a story. So what happens is, by putting in P minus 1 eaten cookies, that's the same as putting in P minus 1 partitions, and now the set has P spots. So imagine we have 8 cookies and 5 people. So C plus P minus 1 is going to be 8 plus 5 minus 1 is going to be 12. Cookie Monster shows up. Cookie Monster eats 4 cookies. Everything up to the first eaten cookie goes to the first person. So the first person gets 2 cookies. The next person gets 0. It's not their day. Next person gets 2. Next person gets 3. Next person gets 1. There's a one-to-one correspondence between the two. And so it turns out that what we're really solving is x1 through xp, their sum is equal to c. Each of the xi is a non-negative integer. You could actually put in some kind of fairness constraint. You might say, you know, Professor Miller, I don't like the fact that person 2 got no cookies. I want to assume everybody gets at least 1 cookie. Or maybe person I gets at least CI cookies. You know, maybe the professor should get at least 3 cookies because he's got 2 kids at home, right? And if you want to put in lower bounds like that, it turns out you can handle it very easily. What you do is you let xi be ci plus yi, where yi is the excess over the forced amount. And it's now the same as just doing fewer cookies. You can apply this to Zegendorf decompositions. So I want to count how many integers between fn and fn plus 1 have exactly k summons. Well, the largest summand has to be fn, and I have k minus 1 other sums. And if I look at the indices I, this is the part where you just kind of look and you don't write down all the details. Okay? If I look at all the other indices, each index has to be at least 2 more than the previous, and the first one has to be at least 1. So what I'm going to do is I'll let ij minus 1 has to be at least 2. I'm going to let the d's be the gaps between the indices. And for each gap, I'm going to take what I know it has to be at least as large as, and then add a little bit more to it. And so when the dust settles, I get the sum of the d's is equal to something related to n, so that the number of ways of having an integer between fn and fn plus 1 with exactly k summons is just going to be n minus k choose k minus 1. We actually have an explicit formula in this case of how many ways it can be done. So we can actually tell you, if you choose a number randomly, what is the probability it has exactly k summons? It's going to be this number divided by the number of numbers in the interval. Fn plus 1 minus fn is fn minus 1. So I presented this at a conference and I said, I haven't proven the theorem yet. Please, nobody in the audience prove this theorem. My students will be proving this in a month when they arrive on campus. They will prove that it's Gaussian, and I don't know how far they'll extend it. I'll have them come down next year to the conference, because the conference was in May and the students arrived in June. So we've seen Stirling's formula before, and in fact told us about n to the n e to the minus n squared of 2 pi n. We can use this to approximate binomial coefficients. And so the students then said, well, let's calculate the probability you have exactly k summons. It's a little bit more algebraically convenient not to go from fn to fn plus 1, but to go from fn plus 1 to fn plus 2. It just replaces some minus ones. And so they just took the n minus k choose k divided by the number of terms, and they just started doing algebra. And more algebra, and more algebra, and then running the effigy as they're doing more algebra, and running the actuality as they're doing more algebra, continuing to do the algebra, and then eventually the algebra ends and you have a Gaussian. And so it is a follow your nose proof. Once you have the idea, once you have the binomial coefficient, it is done. That doesn't mean it's easy to go through it without making an algebraic mistake. There were tremendous numbers of algebraic mistakes. But once we had this, we could then generalize. And it turns out that it's hard to generalize because there's so many things that work out nicely with the Fibonaccis that don't work out with other ones. We actually end up using differentiating identities, the technique we saw earlier, to handle problems like this. But it can be done without too much trouble. And it was wonderful to see the students do this. But you want to get a sense of what are the techniques you can use to attack a problem. And if you have the right perspective, often it's, yes, now we know what to do. And then the hard part is, can you actually get the algebra to work? So I will be sharing with you a paper that I wrote with a student who took probability with me last year. There is a wonderful problem where you have a n by n board, and you want to put down n queens in such a way as to maximize the number of pawns that can be safely placed. There's a lot of different twists you can do. The twist we have is, queens are very powerful. Let's look at rooks. They're powerful, but not as powerful. Rooks attack horizontally and vertically. If we place n rooks randomly, what is the probability that at least one square on the board is safe? And it turns out it converges to 100%. What is the expected fraction of the board that is safe if we place the rooks down safely? It converges to 1 over e squared. Whenever you see something like an e or a pi, you're doing a good problem. So the question is, how do you do the algebra to get a 1 over e squared? So I will send the paper now. It will make more sense later in the semester. It uses a lot of the techniques we're going to develop. It's going to use binary indicator random variables. It's going to use Stirling's formula. It's going to use binomial coefficients. It's going to use variances and covariances. It's going to use expected value, linearity of expected value. And it's a way to try to apply this. But the reason I'm so excited about this problem is, how do you do the algebra so that at the end of the day, you can see 1 over e squared? If you have a closed form expression, that's wonderful. And it's very hard to get. All right, so this is a good place to stop. Okay.